invitation, and it's a pleasure to be here. So I would like to talk today, kind of establish where science is heading in the era of AI when everything is changing and changing so very rapidly. So we are living through a new revolution in science that is transforming really everything. And this whole revolution is driven by Moore's law. So basically, it's an exponential process, and it has been going on for several decades. But essentially, it's based on the fact that the sensors that we use for much of science, which are the imaging devices, are built on the same silicon technology as our computers. So the two can go hand in hand. So the data that we are generating can also be processed. And I had the privilege to work for many years with Jim Gray, and we saw how this is actually changing science and how this is leading to a new paradigm of science. And science is changing exponentially. So we started out thousands of years ago in collecting the first star charts and essentially collected data empirically. And it was going on for thousands of years until Tycho Brahe handed off his data on the motion of the planets to Johannes Kepler, who abstracted a few very simple analytic equations out of this, which could be solved and represented actually all this data in the form of two lines of equations. And this continued all the way until probably culminating in Einstein's general relativity, when we entered the era of computational science. And this started with Fermi and Ulam, starting to run numerical codes at Los Alamos to try to solve some of the equations which were simple to write down, but they didn't have an analytic solution, like the Navier-Stokes equations of turbulence. And today we are entering yet another era, which is data-intensive science combined with AI, which is really synthesizing everything that we know about science, the theory, experiment, and computation together with the tools of statistics. But it requires a new way of thinking, as we will see. And if you look at it, the first stage, the first paradigm lasted thousands of years. The second paradigm lasted hundreds of years. The third paradigm lasted a few decades. This is happening now, here. Science is also changing structurally. So historically, science started out from natural philosophy, and it started to partition fragmenting into narrower and narrower disciplines. So it was first to physical life sciences, earth sciences, then each of those actually subdivided, into theoretical, computational, and so on. But today we see a convergence between all of those, and we see that actually there is this big field of, so basically, for example, there was very little between a computational physicist and a computational genomicist, a computational biologist. They didn't share too many of the tools. And today with the big data emerging, a lot of the technologies of data science and AI are actually very similar, and all the sciences are kind of hanging on the periphery of this. And data science is becoming the new math, the common language, which used to be mathematics. So in the hard sciences, you couldn't run every time you saw an equation to your mathematician friends to solve it. And you had to actually be able to conceptualize your way through the solution. And it is the same thing today with computation and data science. If you want to tackle a real problem, you have to see how you have to organize the data to begin with to be able to get to the end. Tomorrow's scientists are multidisciplinary, but today we are still training people who are typically eye-shaped. Eye meaning that's very narrow and deep. And our whole higher education process is training such people. And as you get older, like I am, you develop a horizontal bar on top of it. You become T-shaped, where you develop a shallow knowledge that you can talk to people, your colleagues in the faculty club. You can go to a colloquium and kind of roughly grasp what's going on in a biology colloquium and so on. But this is not enough today to do competitive science. And new disciplines emerge when two existing scientific disciplines intersect. So for example, when Watson and Crick met, it was a physicist and an ornithologist created genomics. And this happens when these T-shaped people actually were able to talk, the top of the T intersected, and they established a new science. And the students became pie-shaped, who were equally at home in those respective disciplines. So today we need people who are not just at home in their own physics or biology or chemistry, but they also have to understand data science and AI. And we start to see that today the biggest classes at American universities are not the introduction to calculus or introduction to physics, but it's data science and AI. Those are the biggest attendance classes. So we need to start training pie-shaped people, because if later on, if you already get out of grad school, it's too late to grow a second leg. You don't have the time. You have to already run forward in your discipline. This has to start early. Science is changing its granularity. We started out at the beginning of the 20th century with manual production of data, where basically one experiment superseded the other in a few years' time scale in the university labs. And we went to the Industrial Revolution, starting kind of with the national laboratories after the Second World War. And in the 60s, the big science projects started. We started to build CERN, DAISY, the different accelerator labs, starting out really in high energy physics, but followed by other sciences. And these were typical $1 billion projects where it took decades to build the experiments. They were built in a very risk-adverse fashion, because on that scale, you are not allowed to fail. It involved thousands of people. And this is a big difference. So when we have small experiments, then the data sets have a short lifetime because they are quickly superseded by the next one. But when it takes 20 years to build an accelerator lab, and then another 20 years to do an experiment, that data is not going to be repeated in our lifetime for the same experiment, even in an improved fashion. This data is here to stay. And for example, if we look at particle physics, so it started out with the Van de Graaff generator, then the Cockcroft and Walton built the cyclotron, then we built the synchrotrons, which already took a building, and then we built the national labs. And the next stage was the US started out to build a superconducting super collider, and they already built the tunnels in Texas, and in the end it proved to be too expensive for a single country, so the whole world got together to build the LHC in Geneva. And that's where we are heading with these ultra-large projects. But the data is here to stay for decades. But as a result, science has become bimodal. On one end, there were the little research grants, and on the other end, there were the billion-dollar projects. And this was where most of the government funding was going. And the little grants are not big enough to make a substantial impact, except for the occasional big discovery. And the big projects are basically too rigid, too inflexible, too risk-adverse to actually do anything. So they are always, by the time the experiment is created, it's technologically obsolete. The Hubble Space Telescope had smaller chips in it than the IBM PC. So this is changing today, partly because there's a new generation, new source of funding emerging. Some of the big internet billionaires, Eric Schmidt, Gordon Moore, etc., they are providing funding, and they are very impatient. They want results yesterday. They want to fund such science projects. So there is a bunch happening in the middle where they are providing $10 to $100 million grants to much smaller projects. And these are typically creating a unique instrument, are led by an associate professor, somebody in their mid-careers who is hungry and wants to do results very, very quickly. They don't want to wait 20 years to build an experiment. So they are using bleeding edge technology, not even cutting edge, but bleeding edge technology to get the maximum out of the dollars. They take lots of risks, they push the budget to the limit, and they generate petabytes of data. And they are very agile. They represent the most agile part of science today. And it's very important because of the exponential technology growth. Unless you are out at the bleeding edge, you are already obsolete. This is particularly true in AI. And these are highly automated robotic experiments, which are actually leapfrogging over the industrial revolution of science. This is now not even industrial production a la Henry Ford of data, or like CERN is working or Fermilab. These are now really using AI tools, highly automated workflows, et cetera. And this represents the next step in scientific data acquisition. And this liberated an incredible amount of fresh intellectual energy. It was, like the Berlin Wall came down, and then all this energy that was suppressed, it exploded. This is, you can see now at various places. So the lesson is that even small groups today are able to generate very significant high-value petabytes of data using the advanced technologies. And this takes me to how can we compete in this crazy world where there's a mad rush, especially by the big internet companies who are watching over their shoulders what the other is doing and essentially trying to invest, buy hundreds of thousands of H100 cards that essentially universities cannot compete with. And so faculty hires are for 40 years, that says it all. So, but we can compete in tenacity and creating high-value data because the internet, the big companies don't have the patience to actually invest 5 years even to generate a new unique data set that can change science. At the same time, basically the breakthroughs, we can see how the AI breakthroughs came from AlexNet and CFAR, et cetera, in astronomy from SDSS, in genomics from the Human Genome Project. These were actually, so AlexNet was done at Stanford and so on. So these were relatively small data sets, which still required a substantial investment. And these were all combined with a disruptive idea, nevertheless. And so creating such data sets offers academia the best chances to remain competitive in this world, because we cannot compete at the scale in the hardware. And the Sloan Sky survey, this is which got me into this field, thank you, was probably the first such mid-scale project. It started out as a $25 million project where the universities put together some money and also augmented by the Sloan Foundation. Sometimes we call it the Cosmic Genome Project. The idea was to build a very large mosaic of CCD chips when each 2K by 2K chip was $200,000. We started at that time. And you couldn't buy it simply. We had to buy a foundry run from a factory, from Tektronix. And it was supposed to take 4 years to build the instruments and then 4 years to observe the sky. And the goal was to make the map immediately available. It turned out that everything was much harder than we thought. It was not $25 million. We thought it will take $10 million to build the telescope, $10 million the instruments, then $3 million on the mountaintop, and for $2 million we built the software. By the time we actually had data, we were at $120 million. In 8 years, it took twice as long, and half of it went into the software. That was the first big awakening in this mid-scale project. That it's not the iron anymore, but it's all revolving around software and software technologies. And Hopkins signed up to build the databases and the archive, and this is how I got to meet Jim. And we basically ended up building a fairly forward-looking system. So it was, first, the two of us were hacking. There was an official project that was based on an object-oriented database called ObjectivityDB. And Jim came along, and the two of us started kind of hacking away as cowboys to build something more forward-looking. And Microsoft just bought SQL Server source code at the time from Sybase, and Jim was building the Terra server, which was the origin of Microsoft Virtual Earth. And we started to build a big spatial indexing library, which was doing spherical geometry distances in T-SQL. You need a Jim Gray, actually, to code this up. And in the end, this became the official database of the Sloan survey, where we built a visual interface heavily integrated with a relational database. And what we found that astronomers adopted remarkably fast, unbelievably fast. And we saw the emergence of the internet scientists who made serious original discoveries. And we built a collaborative server-side analysis, which Volker already referred to. So And in the process, scientists had to become publishers and curators of the data because we couldn't hand off this library, this data. It was too large to hand off to the publishers or to the libraries or to the typical curators of data. So main concept in the Sloan design, which may actually be of some relevance for our sciences. So the requirements were defined with Jim's famous 20 queries metaphor. So when I first got to meet him in San Francisco, I went to BARC, the Microsoft lab in San Francisco, and Jim said, okay, what are the most important questions you want to ask from your database? And I smiled and said, we are scientists. We all want to ask anything and everything. We don't know ahead of time. Jim smiled, okay, but for the sake of, so write down the first 5. So I scribbled down, give me all the galaxies around this point in the sky within 10 arc minutes. Okay, then he said, second one, and I wrote down something. After 5, I started scratching my head. Then I said, okay, I need to think a little bit more. Then after an hour, I was able to cook up another 3 or 4 of these queries, and then he said that, okay, so now give me the next 10. And I said, no, I have to go home and think about it harder. And so in 1 hour, he taught me humility, the prioritization, and we established also a common language, so which was amazing to see. Instead of writing a 100-page brain dump, for a requirements document without any priorities. The other one was that once we actually built the DDL, the database schema, which was largely derived from the 20 queries, that how we partitioned the data, how we indexed it, how we created views, which views did we materialize, and so on. But then how do we document it? And it was changing, we made iterations, and it was untenable to keep a separate documentation, so we adopted the Donald-Knuth approach. So we used comments in the DDL, in the SQL source code, to actually encode all sorts of metadata. And we parsed it, we ran the DDL that created the schema, we parsed the comments and extracted basically the markup language, and that created the documentation. Instead of doing a traditional ETL, extract, transform, and load, we actually did an extract, load, and transform. So we did a 2-phase load. We first loaded the data as it was, basically in the form of how the instruments organized it and provided, and then we got it in batches, and then we actually retransposed the data and reorganized it in such a way for each batch how it's optimal for the analysis, and this worked really well. We always preserve the hyperlinks to the earlier stages of the data processing. So if there was any doubt, we discovered something, there was, with a couple of mouse clicks on the front end, we were able to get to the raw data related to a particular object. Instead of providing a moving target, we came up with the notion of providing annual data releases. So the data was coming in continuously, but every summer in June, we actually put a checkpoint on it, and we did an annual data release. So the data was, for the public, the visible data was quantized. Even if we discovered bugs in the meantime, we didn't fix them. We put them up on a website that these are the known bugs, but we only incorporated them in next year's data release. And we tied these data releases to publications, accompanying them in a paper in a journal, so make it easy to reference, because this was before DOIs. So we could actually keep track of the usage of the data. The database was integrated with a visual interactive interface, but in the end, we provided a SQL backdoor. So it turned out this was influenced by our visited NCBI with Jim and talked to David Lippman, who was the director then, who showed us a letter to Nature by a Nobel Prize-winning biologist who was complaining about the NCBI interfaces. He said that you are putting mediocre programmers and mediocre biologists to create the front ends who basically restrict the ability of scientists to do really creative research, because you can only use those patterns for the database access that the programmers could think of. This was, drop-down lists and so on. And so we said, let's do plain SQL. People said, you're crazy. Why? Nobody ever will want to learn SQL. Wrong. astronomers picked it up in 6 weeks because they felt there is a new powerful competitive tool. Other people said, no, you will be buried under basically a denial of service attacks. No, we weren't. People actually were well behaved. And we, of course, put some choke points on it and throttling. Anyway, but underlying was a principle that Jim always insisted on, always go from working to working. So that instead of building a grand design that, we design something for 2 years, then implement for 2 years, and then deploy it, instead of we try to go in small steps, we basically made a new build pretty much every week. We learned a lot of lessons and a lot of patterns. We saw a lot of patterns in the usage of people, and we are now trying to convert all of these into formal processes. How can we help in other projects? So the statistical, first of all, we found that the statistical analysis and collaboration is typically much easier with using databases. Because instead of having hundreds of thousands of small scattered files, there is a referential integrity to a database. Collaborative features are essential. We also needed to go beyond SQL scripting. What we saw that astronomers actually learned SQL remarkably well. They didn't use it as a hammer for looking for a nail. They played it as a violin. So they really played beautiful music on it. But with the emergence of AI, there was a limit how much you can do within SQL. So luckily, Jupyter came along at just at the right time. So we integrated the Sky server, what we built with Jupyter. So people could server-side Jupyter computing where they extracted the data using the SQL engine, and then they basically could run anything in Jupyter and later PyTorch and Keras. But everything is spatial. So we spent years building and refining a spatial library that was using a spatial quad-tree. For astronomers, GIS was not good enough because GIS was using typically the planar tangent plane projections and also great circle polygons. We needed generalized polygons which also have small circle boundaries. We had polygons which were like 10 arc minutes times 180 degrees. And it had to be accurate to within a fraction of an arc second. So we had to build our own. And first we did it in C++. That was slow as a dog because the calling interface of SQL Server for so-called external stored procedures was milliseconds. Then we actually rewrote it in T-SQL. That was fast but complicated. And then after Jim pushed actually Microsoft into implementing CLR faster, and our library, we rewrote it all in C#, and our CLR library was the first demo of basically how to use CLR. And we built a geospatial toolkit, which became the origin of Microsoft Spatial. In order to do, we saw that there are multiple access patterns from the data. We always have to do visualization, visual exploration, then an interactive analysis on a chunk of data, and then a batch where we scale out and run a crawler across the whole data set. And they have to support all of those usage patterns. Scale out was much harder than we ever thought, partly because it had to be automated. We had to get the humans out of the loop. Wherever humans were in the loop, they made mistakes. And then it messed up. And it was all meeting, all the different data products were meeting in the database. And if one was off or had a human mistake in the metadata, then it crashed. We had to find a common processing level that is good enough. I don't know how many of you saw Spinal Tap. It was 50 years ago, a film about the rock band where a fake interview with the guitarist who says, look, my amplifier goes to 11. Everybody else's goes to 10. So, in the system, you don't have to build something that goes to 10 or 11. You have to build something that goes to 8. It is not necessarily the very best you can do on each individual part of the sky, but it has to be the best that you can do homogeneously over the whole sky. Okay, so that was the lesson. And earn the trust of the community. And earning the trust is a multi-year process. No matter what, when you put out a new data set, typically you can do the prototype and even deploy it in weeks or months. Then by the time people start trusting the data set, it will be a year or two. We didn't find a shortcut to this process. And managing and moving petabytes is hard no matter what you do. So it was all about a lot of trade-offs, and we have to avoid trying to do everything for everybody. Choose your, basically, priorities well. So we started to apply these patterns that we translated into processes. So the slope survey was the first. And today we are actually at 5 billion web hits, 800 million SQL queries that people typed in. These are outside the robots. We have 10 million IP addresses who have been using the data, published 13,000 refereed papers, and 770,000 citations. For astronomy, this is huge because the whole community is only about 15,000 people. Then in 2006, we started to build a database for turbulence. Hydro simulations are done on supercomputers. And we came up with a new metaphor. So these were simulations where we run the simulations for 5,000 times. We extracted 5,000 snapshots. And people wanted to analyze the data, but the only way would have been to download the data, which was, even for our smallest data set, it was 20 terabytes. So we decided that this was the time of the movie Twister, when people drove up with a truck to the tornado and shot an accelerometer into the heart of the tornado. Said, why can't we do this actually in a database? Have the 5,000 time steps, use it as a spatial index, a key-value pair, a key-value server, and then have the users take their laptops and shoot 10,000 sensors into the simulation. And each sensor then extracted the interpolated velocity or pressure or dissipation around it, and return to the user. We did that with a great success. Users came back, so I actually want to move this particle, these sensors along with the flow. Can't you do, why do I have to do it on my laptop? Why don't you do it for us? So we actually gave the notion of movable sensors, so we could pin down a sensor, make it Eulerian, or make it a Lagrangian sensor, which was just going with the flow. And you could pick, so the users didn't know at this point whether the data is a petabyte or a terabyte behind it, as long as it came back quickly. It's a lovely metaphor. And now we have almost a petabyte of data in there. And hundreds of papers have been used using this. And we just delivered actually 400 trillion points to the community over, I think, like a month ago. Then in 2016, I started to work with cancer immunotherapists who are trying to understand how the immune cells are attacking the cancer cells. And they were taking data, a couple of random spots on a microscope slide. But to understand the dynamics, we needed to create very detailed spatial maps where you basically take multicolor images, segment it into the multispectral images into cells, and then classify them as tumor cells, immune cells, look at markers expressing certain antibodies which drive the interactions. This is not that different from astronomy. So we take multispectral images, segment it into stars and galaxies, try to look at the spatial clustering patterns. So we ended up building a database, except that instead of taking 10 random spots over the slide, we completely covered the slide with a mosaic, so we were taking 1,000 times more data. And again, last week we exceeded 1 billion cells in our database, where for every little cell in there, we have the contour stored as a GIS polygon, and also the membrane as a GIS polygon. So I can type in a SQL query, which gives me all the neighbors for all the cells which touch each other. And on our first experiment, we actually discovered a predictive biomarker that can predict whether a patient will respond to a drug for melanoma. So each cure is about $150,000, and only 1 in 5 people respond. So this is basically figuring out who are the patients who should be served these drugs, and potentially discover that for the rest of the 80% of the people, what other drugs maybe have the same effect. So, and we are moving into ocean circulation models using similar technologies as the turbulence, that how can we actually visualize interactively and launch sensors floating, which are moving now in 3 dimensions in the ocean with a 2.5 petabyte data from which represents a 1.5 kilometers resolution for the whole Earth and the 1-year circulation model. So using similarities for the Sloan, we were actually able to recycle a lot of these technologies and over. So what is the common in these? And it's worthwhile looking at the music industry. It's because it's a good example. And also because it's happening, and it happened in the world, like it or not. And many of the music publishers didn't like what happened. So how did I listen to music in the old days? Went down to Virgin Records, bought an LP. Miles Davis took it home, played it on my record player. I owned the LP, I owned the device. Then came iTunes, where I could actually buy things one song at a time, but I still was the owner of the digital copy, and I played it on my own device. But today, what we see emerging is Spotify and Pandora, where everything happens in the cloud. I don't even know how the individual songs are encoded. It's negotiated between my endpoint, my cell phone, or whatever I use to listen to it. It's all happening in the cloud. What does this have to do with data? We are going the same path. We used to take tape drives, or we used to take tapes from the mountaintop and take it home and from the telescope and analyze it at home on my own computer. Or with Sloan, we sent around actually whole servers containing the Sloan database, SneakerNet, as Jim called it. Then what is the iTunes equivalent? These are the SQL databases that we built. There is a big archive, and I can type in a SQL query, which gets the data that I need for my next paper, one song at a time. Okay. So this is exactly but I still have to do the analysis on my own machine. And where the Sky Server model and Google Colab, and now the Sky Server, which is the generic version of the Sky Server, is heading, is run everything in the cloud and just get a stream of the results, essentially, in your browser. And so this is, but in order to do this, to deal with this cloudy environment, science codes need to pretty much run anywhere. We have to do this opportunistic computing. We have to be able to take our compute where we can get the cheapest cycle. And Ryan Abernethy from Columbia, he calls it ARCO, that the scientific software needs to be rewritten to be analysis ready and cloud optimized. And this is not easy. So we have to be able to use object stores, S3, et cetera, instead of the usual POSIX. Data. Oh, I need to do the. How can we measure the usefulness of data? We first have to, there are three components: the value, cost, and price. We think we know what is the value of data. It leads to new research. It accelerates testing ideas, find targets for follow-up, et cetera, and it provides the basis for reproducible science. So how can we measure it? And it turns out that to use somebody else's data still costs money. I have to pay students, postdocs, et cetera, who work on the analysis, spend a year or whatever. So typically, an astronomy grant today is about $300K for over 3 years. So $100K a year. And if we generate one paper a year, it's actually, that's a fairly good return. So typically scientists spend, my postulate is that around $100,000 per paper. Maybe it's in some areas, some papers are 10,000, but very few of them are $1 million. So 100,000 is kind of a reasonable number. Every paper that is using a different data set is a $100,000 vote on that data set, on the utility of that. What is the price of a data? How much did it take? How much did the experiment cost that was producing it, both the construction and the operation of it? And so a new electron microscope is somewhere between $10 and $50 million. For the Sloan Sky Survey, we are still operating, and we are now over $200 million over 20 years. The LSST, the Rubin telescope, which is just being built, doing time domain astronomy, will be $1 billion. Hubble, CERN, they are in the $10 billion range. And all that remains for this investment at the end of the project is the digital data, is the binary data. Because we will have to strip down the experiments and shut them down when they are completely obsolete. What is the cost? The cost is maintaining the data once the experiment is shut down. And so far, we can kind of cope with until the project is alive, and then we can do it on the margin of the experiment, running the experiment. But the experiments will reach the end of their lifetime, and the data and all this value, these hundreds of billions of dollars of investment, are going to be in the data sets. And people are, waiting to actually use it for various AI training. And the data is offered through smart services. And the question is, who will take ownership of it? Who will pay for it? This is all the bad disks, all the failed disks on Sloan, 1.1 tons of disks that failed over the 20 years. But this is the easy part. The hard part is the salaries of the people and preserving the knowledge. So we need still a trusted intermediary between the data and the scientists who operate these services. And if I compare for the Sloan, so basically the cost of maintaining the Sloan archive today is about $500K per year. The price was about $200 million, and the value is in $100,000 per paper. If I just take round numbers, compare the last two, so 10,000 published papers have a value of $1 billion, which compares favorably with the $200 million cost of creating the data. If people write just 5 papers a year, the archive already paid for itself. And this is only 0.25% of the cost of creating the data per year to maintain the archive. So if we only saved 5% of the survey cost or survey price, we could cover the data for 20 years. And if we thought about us putting in 5% of the running cost of the survey every year into a retirement fund, then we could run it forever because of the compound interest. And this is like retirement. We know that the day will come predictably when the experiment will retire, but the data needs to live. How does the emergence of AI change all this? Much of the AI in science today is related to the posterior analysis of the existing data, through proxy simulations, training AI to reproduce the Navier-Stokes solvers or cosmology solvers or cloud formation for climate models. It's about recognizing patterns, image segmentation, AlphaFold, denoising, doing image compression or discovering correlations or creating some anomaly alerts. There are interesting developments with LLMs. They can recite much of the literature at the same time they also hallucinate. So how can we use the LLMs in innovative ways? One area where we have completely failed in capturing the output of science is the so-called long-tail problem. So if the projects like CERN or Sloan, which have a substantial budget, they build their own archive. But much of the scientific output is appearing as an appendix or a table in a paper, which is getting posted on the web. Some of it doesn't even get posted, stays on the lab computers or on a website, which kind of erodes over 2 or 3 years. And with the LLMs, we can actually crawl the whole corpus of the scientific literature. We can crawl the archive. And we actually understand the context. We know quite a lot about those because we have, for example, for scientific papers, we have the authors list. We can also crawl the papers of the co-authors, et cetera, of the web of authors, build up a special ontology for this. So we could actually use the LLMs to create an indexable and searchable things for all the scientific data that was attached to any scientific publication. We could do this actually very quickly. The whole archive content is actually not that large, a few terabytes. We could do automatic code generation. The way I work, for example, in Jupyter, that in data exploration, I kind of take a chunk of data, roll up my sleeves, and get into Python, and then write a whole bunch of experimental code. I try out 10 different things, starting from my initial data. And in the end, I found one cell in the notebook that actually does what I want it to do, and all the rest is garbage. Then I spend a day in cleaning up my code, probably introduce a bunch of bugs in the process. Wouldn't it be nice to have actually just a push button to have Copilot take the minimum spanning tree of my dependency graph? It's doable, just So I hope that I will have some time to actually write the code behind this button and use Copilot. And it will probably write a nicer code than I did. But nature is sparse. So most of the natural process is dominated by a few parameters. This has been known, from the work of Candice and Donahoe, et cetera, and Terry Tao about compressive sensing. So that was the big breakthrough in compressive sensing, which enables signal reconstruction with much less data. We have these huge neural networks, which actually, in many ways, have so many more parameters that they overfit. At the same time, they don't for some reason. And why? And it turns out that one of the problems in subsampling data is if the data is very non-Gaussian and skewed, and many of the real-life data have sharp edges, especially in imaging, et cetera. How do we sample those without losing the details? And this is, the random projections come to mind. And in a sense, having the many layers, which each of the layers is doing actually a random projection. So once we are 1 or 2 layers into a neural net, everything is Gaussian. And this is contributing to the incredible robustness of the neural networks. We need explainable AI. We need to know what is happening inside and have to be able to attach an error bar. The physics of AI is emerging as interpreting how the neural networks learn and how similar to this phase transition ongoing in spin glasses. The initial random weights of the network develop wrong-gauge correlations. Basically, the eigenvalues of the weight matrices are actually developing a long tail. And we can identify symmetries in the problems looking at the latent layers of the autoencoders. So this is, I think, where a lot of the energy is going to be spent, is already being spent. But there is an area which people haven't paid enough attention to. If I asked any of you, do you have enough data or do you want more? Okay, I don't think there would be any person who would say that I don't want any more data, I have enough. But it's actually the wrong answer to an ill-posed trick question, because I didn't specify what data would you get if you want more. What you implicitly think of is that I want to get more relevant data for my science. You don't want just more junk to sort through. So there's this delicate trade-off emerging, which is where we are starting to get too good in capturing data. And these days, sometimes, or often we make the mistake of collecting data first and thinking about what do we do with it afterwards. Okay. So if one extreme is if we store everything and then we go bankrupt because the whole science budget of the project is going to be spent on these drives. The other extreme is that we don't capture enough data and then there's not enough for the science. But we are approaching a critical point with some of the ongoing projects already around the world. There is an interesting lesson from the LHC, from CERN. While they were building the magnets, the particle physicists, so the challenge is to find a needle in a haystack. And what they don't know what the needle looks like. Okay. They are the Higgs particle, and now what is beyond the standard model. But the particle physicists, by and large, know what the hay looks like. So they built Monte Carlo simulations for 10 years while the magnets were built that were able to create a large pool of events, detector events, which are hay. And then they built filters right at the detector on the edge to eliminate those, so much so that they only keep 1 out of 10 million events, and that is still 10 to 100 petabytes at CERN. So instead of having to store 1,000 exabytes. So these trade-offs are essential. We cannot do everything for everybody again. And we have to be able to eliminate, the known science or reduce the known science, whether it's, not 9 or whatever number of 9, 7, 9 to 1. It could be just 99 to 1 or 999 to 1. But we have to start doing something. How does AI help? So basically the particle physicists did the hard way. They just coded a lot of Monte Carlos. Today we have better and better tools for diffusion models doing various generative AIs, where we could take basically the AI technologies, and for each of our respective science projects, we train the AI, the generative models to recognize what is the known science in our discipline, and then essentially run an autoencoder where we understand what is the boundaries, what is the affine Hall in this latent space of the known science. And if something is inside there, we subsample it, either throw it away completely or subsample it to 1 to 100 or 1 to 1,000, and just keep everything which in the unknown domain, because that's where the most exciting stuff may happen. And this can have a much bigger impact on science than actually running all the posterior things on the existing data sets, because we can go much farther in the tail of the rare phenomena. So in a sense, if an AI algorithm can drive our cars, why cannot it drive our microscopes and telescopes? And it's coming. And this is coming to the experimental design too. That not just reading the data at the edge, but actually what are the experiments of the zillions of things that we can do? Why don't we, if we can formulate our science goals in terms of a cost function, we can use the AI to actually define what the next observation should be made, given our existing information and the things that we want to measure. And we are trying to do this right now on the Subaru telescope with the help of the Schmidt Foundation. So basically put the telescope into a reinforcement learning loop. As we start observations, we keep weeding out and iterating and improving our target selection algorithms using AI. Very end. In the end, there's a lot of technology, but the big challenges are really, in order to get there, they are primarily not technical. And there is a data life cycle, but once we are producing smart data, there is also a service life cycle. So there are people involved, and the operating system change, technologies change. The data is becoming increasingly smarter with AI. But these platforms need maintenance. We can't just drop the data on the disk and be done with it. It has to be constantly being evolved and improved. Moore's law is there. And they follow the technology. So today, much of the open science data today was paid for, had a price more than $100 billion in investments. And it's a national treasure or a world treasure, and it must be preserved. But there is a conflict with the short-term federal funding cycles, especially in the US, where the federal government is unable to make a 40-year or 20-year commitment to these long-valued, very high-value data sets. So they struggle their own ways, and the different federal agencies each try to do something which is all different. And this is a too big problem for any of the agencies to solve on their own, but they don't coordinate. So it's a total mess. And there is an example of how to do this right. The Smithsonian, which stores in the US the physical specimen of the greatest discoveries for the last 150 years. And it started with a private donation, which was eventually augmented by the federal government. So where is the Smithsonian of data? And we have to do it, and I think in Germany there is actually, I think there are some good ideas around there with the what is it called? The DFAI, yeah, okay. Anyway, so the challenges are really non-technical. Summarizing quickly, we have the 4 paradigms of science, and the data-driven AI is the 4th one. But I think at the point when we are handing over the control of our experiment to AI, that may be the 5th paradigm, and the decision-making is also handed off to AI. The organization of science is changing. We see the mid-scale emerging, which is accelerating science and increasing the agility. There was a vacuum, and scientists naturally fill in the gap. We need to be aware of how ridiculously cheap it is to preserve the data, yet we are not doing anything about it. The emerging AI is changing everything, but we need explainable AI to actually be able to attach significance. We need to collect more relevant data, and all of today's science ends up in digital data. And we will not do something about it until there will be a major embarrassment and one project will lose, get its data, $1 billion value data gets corrupted. There will be then a congressional investigation, and 5 years later, there will be probably some action. What we have today is this ocean of data, and the sun is rising. But it also helps us to understand how immense the challenge is. Thank you very much.
So thank you very much, Alex, for this fascinating overview of, on the one hand, the history of the Sloan Sky Survey and how it evolved, and bridging this forward to the challenges that we see today and how past solutions can help and where new frontiers arise. So we have time for questions. So are there any questions? So while people start to think about it, I think I hear some, or I see some already, but so I had one question also in my mind, and that is, so we had talked many times about the importance of declarative languages in order to enable those kinds of infrastructures, because you need to specify what you want, not how to compute it in this complex infrastructures. Yeah. This works well, or worked well in the Sloan Digital Sky Survey, since you had effectively those SQL queries that you could run, right? But if we now move forward to AI, how do you see this still is possible, or how does this work, since SQL alone may not be enough anymore? You alluded to that already.
It's clear it is not, and I think that's a challenge with the emerging, with the machine learning frameworks and so on. So we need to have, something like what you worked on so many years. So, but it's clear that the scientists will, first of all, the hardware platforms on these codes will be so heterogeneous and also so complex, the users cannot be expected to be able to set up the iterators explicitly, so the system has to optimize itself. So.
Thank you. Then there were some questions. First one here. Yes, please. Yeah, you. Hmm?
My question's actually back one slide. The U.S. agencies that are struggling to manage their data, well, first, would you trust the U.S. government, Congress, to implement some policy that you'd actually trust for them to have a centralized repository? And conversely, a lot of those agencies, you could argue that the process is working as intended, that the struggle for finances causes them to get rid of the data that is unimportant, to boil the data down to the most important pieces. And without that sort of crucible, we all know, all of us, keep notebooks we don't need. We keep tons of data because it's much easier to just keep than get rid of. So boiling it down is part of the funding process. But I wouldn't trust Congress to try to enact some kind of data preservation policy. Would you?
No.
So
okay, let me answer the second part first, which was how to decide which data to keep and which data to throw away. So in a sense, this was driving my attempt to assign a dollar value to each of the components playing in that equation. So to translate all the relevant aspects, the price, the cost, and the value into a common currency, that you can make a rational business decision. So that if a data set that doesn't generate 5 papers a year or so, then that probably should be not deleted maybe, but put into a cold storage. So that's the second question. First is trust. Well, we know that Trump was, I think, inaugurated on a Friday, and Monday morning they were already starting to delete data from the EPA website. Okay, that says it all, how much you can trust the federal government. So the system searching, I don't think there is a way to put all this digital data, which is generated exponentially, into a single location, because by the time you move some data to a central location and establish, the protocols for it already, using a newer technology, 3 other projects have sprung up in another part of the world. So it will be inherently distributed somehow, and we have to figure out a way to deal with it. And maybe, okay, what is the largest organization in the world preserving cultural information? Probably the Catholic Church, but would you trust the scientific data on the church? Probably not. The second longest lived are the university libraries, who are trying to reinvent their mission, because the card decks and the shelves of books are thing of the past. So maybe, you know, a whole network of university libraries worldwide could actually start to fulfill this role. But it has to be fault tolerant.
Yeah, so this is along the lines of what you were already alluding to with this national research data infrastructure in Germany, where there's a good amount of discussions on that. So any further questions? Yes, please. Mm-hmm.
Yeah, thanks a lot for the talk. So I really like your statement that we need to collect more relevant data, and I totally agree, because a lot of people now focus only on the quantity. When I think about relevance, I think about high quality. And for example, I work in agricultural sciences, and we need to think about data, what we should collect. And do you have any opinion or statement on which quality criteria should we focus on? So how can we know beforehand which data is important, what should we actually really collect on the field, or not only what to keep?
I don't think there are general, okay, so first of all, it's with the Sloan data and the virtual observatory, we thought long and hard, how could we create some refereeing of data? And there's nothing better than actually get it out there and let the community decide, and kind of somehow capture the trust, the built-up trust of the community somehow, and have the community help, for example, debug the data. But there is no such thing as data police. I don't really see as a viable, we sort of various mechanisms, and we came up blank. So.
Sorry. Thank you for this interesting presentation. I was wondering, maybe back to the start, you talked a bit about the advantage of the agility of like new private entities funding research, but I was also wondering, do you see risks associated with these emerging players, especially when we think about open data and science and explainable AI, which some like private institutions wouldn't have the interest in kind of promoting that necessarily, or also thinking, now that we talked about the Congress, I thought back of the 70s where maybe some information on climate change was already privately investigated but not published in that way. So yeah, I was just wondering about like if you see potential risks besides the improved agility with privately funded research.
So I think many of the private foundations, and here I mean Schmidt, Moore, Sloan, Simons, you know, these are the big American foundations. They are all individuals whose kind of ethics is completely, you know, above standards, and it's not Exxon so it's not the commercial companies or the big pharma who would finance. So I think as far as these people are concerned, they really want to get science out in the open entirely, and they are all for open code, open science, open data. And they much more probably even than the government. The government is doing a lip service, and these guys actually trying to make this happen. And there are, of course, then the various foundations with a political charge. That's a whole different ballgame. And yes, there are dangers in there. But I don't think they are investing all that much money into science. So.
Yeah, I mean, I guess I was also wondering about like big tech, because you were talking about that too, kind of investing more in AI research.
Well, I think big tech, so say Google, okay, DeepMind, etc. So I think they did something very cool with AlphaFold. In general, they only pursue a science project until they get a front page of the New York Times. And then their patience runs out. And I collaborated with Microsoft, collaborated with Google, etc. And Amazon, and we got sometimes, free allocation because there was somebody in the upper management who was interested in science, and they gave us half a terabyte of storage, which was not really enough to do anything serious. We still put up some data there to try it. Then by the time we finished putting the data there, the person moved sideways, and we were told that you have 2 weeks to take your data away before it gets deleted. We did this 3 or 4 times, and then we didn't bother any longer. So,
thanks.
Hi, my name is Rodrigo. I work at JUA. My question was a bit about licensing, and if you think licensing could be a good tool to kind of align the usage of data in this open context towards the producer's values, or?
Well, if you mean a commercial license, then probably the answer is no, or at least, okay, so there is FAIR. FAIR is wonderful, but science is more than fair. In a sense, it needs to be also free and sustainable. Because FAIR doesn't say anything about the cost, that whether you can charge for the data or not, it's about interoperability and so on. And if you charge, and in science, if the government is not funding a data set, an open data set, either somebody has to pay for it, okay? And then if somebody pays for it, the question is, how do you sustain it over 20 years? And I can't imagine, asking for a credit card number if you wanted to access to the Sloan data. I think we would get first a couple of rude emails, and then people would walk away. So that's just not in the mindset of scientists.